Well, as a quick review, what I would like to do is talk about a little bit about what we have done already. And if I was going to put that in a fairly small nutshell, I would say that we have looked at the transient response for RC circuits and RL circuits. That basically means circuits that have a resistor and an inductor, that's an RL circuit, or a circuit that has a resistor and a capacitor in it, that's an RC circuit. We have looked at what the response is for those kinds of circuits when there is already some sort of charge of energy in the inductor or the capacitor before you ever get started letting the circuit do its thing, okay? And we kind of see what happens if they already have energy in them, and then we hook up a resistor across them and see how that tends towards zero. So that's what we've done so far. But there's another possibility that can happen with inductors or capacitors, and that is they can be hooked up into a circuit where the elements in the circuit are trying to actually put energy into them, okay? And so the first thing we did, where it was energy that's essentially being bled out of inductors or capacitors, that is what we call the natural response that happens for those kinds of circuits. And today what we're going to look at is called the forced response. And the forced response is essentially what happens when you hook it up into a circuit and the circuit tries to drive the voltage or current, depending on whether you're talking about a capacitor or an inductor, tries to drive that value to some other value than zero. Okay, so that's essentially what we're trying to do today. And so by way of sort of showing you how this works, what I would like to do is set up one of the most simple circuits that we possibly can, and then run through the nitty-gritty math in order to kind of come up with what is this forced response going to look like. And the one that I'm going to present to you is this this circuit down here that has a current source that, if you kind of think about how this circuit would work, you've got a different kind of switch here, right? This switch is set up so that it is connected in one position before time zero, so that it essentially allows this little current source to do essentially a very meaningless thing and just drive current in this little loop over here on the left, right? But then at time zero, that switch moves over, and then what will happen? Well, that current that is being supplied by that current source, instead of going in this pointless little loop, now is being driven over here, and it's going to be split between, some of it might go through the resistor and some of it might go through the inductor. And then what we're going to do is see over time, how does the current behave in the inductor? Okay, before I even get into the math of that, what do you think happens right at first? Okay, I've said here at time zero, we're going to assume for this example at least that the current in the inductor is zero. Okay, so right when the switch flips, right, in other words, going from 0 minus to 0 plus, at 0 plus, how much current you think is flowing in the inductor? Zero, and how do you know that? Because current can't change instantaneously in an inductor. So even before we try to do any math, we can look at that and say, we think we're going to start off with zero current in the inductor, right? And then what should happen is maybe that will start to change as time moves forward. And we're going to try to come up with a function that tells us what that current is in that inductor as a function of time, okay? So step one for this. Let's actually look at this circuit after the switch flips and try to think of it as this special kind of circuit that we've given a name before. It's called a single node pair circuit, okay? What that means is that once that switch flips up here, right, and basically makes this connection, instead of being down in the position shown, it has essentially made this connection up here like this, right? What that tells us is that all three of the circuit elements that are playing here, the current source, the resistor, and the inductor, all three of them have the same voltage across them at all times, right? And I'm calling that V as a function of T, because that might be an interesting thing to use when we start setting up our circuit analysis. And as a matter of fact, what I'm going to do is I'm going to say that's the voltage across all three, and what I'd like to do is a Kirchhoff's current law analysis on the upper node. Essentially add up all the currents leaving the upper node set it equal to 0, and see if anything interesting comes out of that. Okay? And so that's what this first equation is that I'm showing right here at the bottom of the screen. We have IS being the current source that is entering the node, so it's a negative value. Then we have V of t over R. That's the amount of current that would be flowing out of the upper node through the resistor. Then we have I of t, which is the current that is flowing through the inductor. Okay, with me so far on that? Well, here's the cool thing. Because we have this inductor over there, there's a relationship that we are allowed to use for voltage relative to the rate of change of current for an inductor, right? V is equal to L di dt, okay? That's the voltage across the inductor is going to be the inductance times the rate of change of current, okay? Now, because it's a single node pair, that means that the same voltage that's across the inductor has to also be across the resistor. So where we had this term right here, right, the one that had the Vt over R that's based on the resistor, we don't care that that Vt, we're thinking of it as the voltage across the resistor because that Vt is the same voltage that's across the inductor. Do you agree with that? Because it's a single node pair. It's got to be the same voltage across those two elements. And because of that, it allows us to do a substitution using V equal L di dt and basically substitute in L di dt where I had V. And if I do that, that middle term ends up looking like this, L over R times di dt plus I. So anyway, the new equation is minus Is plus L over R di dt plus I is equal to 0. Okay? And just kind of similar to some of the other times that I've done this, a lot of times through the middle of a derivation, I might drop the notation of t, right? The little parentheses that denote that I is actually a function of time. We should understand that I is a function of time, and we should understand that voltage is also a function of time. So that's why it's, sometimes done to make your notation more compact to just eliminate the of t part of it. All right, so once I get this essential equation that's at the bottom of the page, we can rearrange that a little bit and isolate di dt on the left side. And what we would have on the right side, once we isolate that, is minus R over L times I, lowercase I, that's I of t, right, minus Is, which is the current source current, right? So this is what we would end up with right there. The next step is called the isolation of variables. Okay, that basically means I want to get anything that has to do with current as a function of time. I want to bring it all to the left side of the equation, and then everything else I want to put to the right side of the equation. Okay, when I do that, what I end up with is what is inside of these integrals. Okay, now since I wrote the integral on there, it's not hard for you to see that essentially I am going to then integrate what was inside of each of these integrals. Okay, so essentially divided through by I minus Is, right, multiplied through by dt, and then took an integral of both sides. On the left side, since we are dealing with currents, I have to integrate for current values, and I think I may have put a little, had a little error right there. That should be di. Excuse me. Anyway, I need to integrate from whatever the current value is the inductor at time 0 up to whatever the current value is the inductor at some arbitrary time t. Okay, on the right side, I am just integrating from time equals 0 to time equal t. And so when I do this, what you end up with this 1 over a function of the variable that you are integrating with, what you end up with is natural logs. Okay? And because I have two limits of this integration, I basically have two natural logs that I would have. The one that's on the left would be what you get out of the upper limit of integration, and the one that's on the right would be what you get out of the lower limit of integration. Okay? On the right side, integrating R over L dt from 0 to t is pretty simple. All you end up with is minus R over L times t. Okay? Now, In order to undo natural logs, the easiest way to do that is to essentially take the natural log and raise it as the exponent of e. I really should be careful how I say that. You use it as the exponent of e, right, in order to essentially undo the natural log. And so that's kind of the next step that you see there, is I took that entire expression, made it the exponent of e, and I did the same thing on the right side. I took what was on the right side and used it as the exponent of e. Okay? Now, when you have a difference in the exponent of e, or of any value really, what you can do is you can take basically a fraction of the two parts of that subtraction, right? You could take a fraction, e to the first part of the subtraction, e to the second part of the subtraction in the denominator, right? So that's essentially what we get right here, is I can split those two parts away from each other. And when I actually do that e to a log, what you end up with that is just whatever was inside the log to begin with. And that happens in both the numerator and the denominator. And so that allows you to boil out just I as a function of time minus the current source value, right, over minus the current source value is going to be equal to, again, e to the minus r over lt. That side didn't change in that step. Okay? So then what's next? We can then rearrange that expression slightly and isolate the I as a function of t. Okay? And if we do that, what we end up with is an expression that says it's going to be the current source value multiplied by 1 minus e to the minus r over lt. Okay? This is going to be valid for time greater than or equal to 0. Because what happened at 0? The switch flipped, right? And so this function right here essentially gives us, you know, a way of expressing what will happen with this current for time greater than or equal to 0. Okay? Now, that's only of a certain amount of value to kind of see what a mathematical function might consist of in terms of the variables that are in it. What helps us to feel this a little bit better is if we actually put some real values in it and we try to see what would that look like for an actual circuit. Okay? So let's say that the current source value, let's say I'm doing this now for a specific circuit. So let's say that the specific circuit I'm doing it for has a current source that is supplying 10 amps. Let's say that that's being fed across a resistor that is 1 ohm and an inductor that has a value of 47 millihenries. Okay? With me so far? What happens if we flip this switch is that the current in the inductor is going to, this is what this function up here says will happen, right? The current in the inductor starts out at what value? 0. And just a few minutes ago, that's kind of what we said intuitively. We would expect we should start out with 0 current in that inductor because it can't change instantaneously. Okay? But then what happens? Okay? It starts to increase, but as it increases, its rate of increase decreases. I know that kind of gets confusing to say things like that, but it's essentially start to increase quickly, but then the rate that it continues to increase starts to slow down. Okay? And what value does it eventually hit? 10 amps. Okay? Do we expect that also? Okay? So let's think about our rules for steady state, right? Our rules for steady state say that if you leave something connected for a long time, capacitors look like open circuits and inductors look like short circuits, right? If we put a short circuit there where the inductor is, then that would make it so that none of the 10 amps would flow through the resistor because it has an easier path to flow on. That would be the inductor, right? So all of that current will eventually flow through the inductor if you leave it connected in switch state 2 for a long time. Okay? Does that kind of make sense? So I would say that I like this because everything makes sense about it, right? Starts out at the right place, ends up at the right place, and it kind of makes sense even the middle part, right? Because what happens is how much voltage you put across an inductor is related to its rate of change of current right? Well, as we let less and less current go through the resistor and more go through the inductor, you're going to have less and less voltage across the resistor. That means the rate of change of current is going to start decreasing from the very beginning, right? And that would lead to this curvy shape. So anyway, everything about it seems like it makes sense relative to what we know as far as what the inductor should do. Okay? So this is the idea of a forced response. And there is, as I said earlier, there is another video that is going to be available that essentially shows this same type of development for a capacitive circuit as opposed to an inductive circuit. As a matter of fact, that's what I put down here, is that I could write the exact dual of this circuit that I just did, okay? And the exact dual is essentially, instead of a single node pair, it is a single loop circuit with a capacitor in it and a voltage source going through a resistor, okay? And it turns out that if you do a very similar derivation to what I just did right here, you can come up with a result that looks almost identical to the result that we came up with for the inductor. Okay? So this is some pretty handy stuff. Now, it would be nice if we could always expect that we would either have a purely natural response kind of a circuit where, it was something where you had an initial charge in a capacitor and it would just discharge through a resistor down to zero energy, right? Or if we could expect that in the real world, it would only be a purely forced response. In other words, starting from zero and going up to some value like we just looked at. But how do things tend to work in the real world? It's probably going to be a combination of these two effects, right? And so what we want to do next is show you an example of how you might have a combined circuit where instead of it starting at zero and going to something, or starting at something and going to zero, we're going to start at something and go to something else. Okay, neither one of which is zero. Ready for this? But this one I'm going to do as a capacitive circuit, and so we're going to have to keep in mind this function that I told you exists for a capacitive circuit. We're going to have to keep that in mind to some level as we work through this. Okay, here's the circuit that I want us to look at. Let's say that we have this circuit over here where Vs feeds through R2 and R1 with a switch up here that would have the effect of shorting R2 at time zero. Okay? And let's figure out, kind of like we've done in a couple of our circuits, let's figure out what our steady state was right at time zero minus. In other words, right before the switch closes. What is going to be happening in terms of a capacitor voltage? Okay, is that fair enough to kind of think of doing that? Okay, so what I did here is I drew a picture of what the circuit will look like at time zero minus. And you'll notice the capacitor went away. Why did the capacitor go away? Okay, capacitors, when you get to steady state, look like open circuits, right? And so I essentially treated the capacitor as though it essentially has these open terminals right here, because the capacitor looks like an open circuit. Because it had been connected in that way for a long time, the capacitor is behaving now like an open circuit. Well, my question is, where is the capacitor voltage going to be seen on this before the switch closes version of the circuit? Is it just going to be the voltage across those terminals? Right? I'm going to say this is the voltage in the capacitor at time zero, maybe zero minus like this. Okay? And let me just go ahead and say that's what that, how that would be polarized, something like that. Remember that we also have another variable that we sometimes use for this, V sub 0, right? That's another way that we sometimes describe what that initial voltage is in the capacitor. What is that initial voltage going to be in the capacitor? Okay. How do we go about finding that? Let me give you a little tip, all right? Because the capacitor is behaving like an open circuit, if I was to try to find the current when it's in this state that flows through this little resistor right here, what is that current value going to be? 0. Why? No place for the current to go, right? So I'm going to say this is I at time 0 minus is going to be equal to 0. If I at time 0 minus is equal to 0, what's the voltage across that resistor R? It's also going to be 0 because you need to have current flowing in a resistor for there to be voltage across the resistor, right? So I can say here there's 0 volts across this resistor right here, right? 0 volts. If there's 0 volts right there, then is this V0 that I just identified right here, does it exist anywhere else in the circuit? Yeah, okay. It is actually the same as over here. Why? Because there's no voltage drop across R, we better have the same voltage on the outer terminals as we had across R1 right there. That kind of makes sense? Okay, well, what voltage is that going to be across R1? Actually, I'll go ahead and put that here. This is going to be equal to VR1, right? But what is that going to be? Is there a quick and easy circuit analysis technique that we can use to figure out quickly what that voltage is across R1? Voltage division, right? We can look at that and say, well, really what we're doing is applying a Vs across a combination of two resistors. And what that is going to imply as far as the voltage across resistor 1 is that it's just going to be equal to Vs times that resistance value R1 over the sum of the two resistance values. Okay? So, essentially what I've shown you here is sort of the beginning part of it, and it's just to figure out more or less what is the initial steady state of the circuit. Now let's get into the next part that's also kind of interesting, and that is after the switch closes. Okay? I showed you a picture here of what this circuit would look like after the switch closes, and you'll notice one of my circuit elements went away. Which one? R2 went away. Why is that? I shorted it. Okay? Makes it irrelevant because any current that flows is going to choose to flow on the switch because that's a zero resistance path. None of it's going to want to flow on R2 once it closes. Okay? So that R2 went away, and we're left with essentially everything that was to the right of that. Let me actually mention this too. R1 even becomes slightly irrelevant to our questions here because Vs is going to hold a particular voltage across R1 regardless of what R1's value is. Kind of see that, right? It doesn't really matter what R1's value is. Vs's job is to hold a particular voltage across that R1 resistor regardless of what R1 is. So it actually turns out R1 becomes somewhat irrelevant to our question also. Okay? So let's think about a voltage loop then that essentially goes around this way, right? Kind of the way I drew it is I started here and went around this loop. Okay? And when I did that, we can look at the voltage on the source being minus Vs. Then I have the voltage across R, which is just going to be equal to the current through R times the resistance value itself. And then I'm going to add the voltage across the capacitor, which is the thing I'm trying to analyze. That's what I'm trying to figure out, is what is this voltage across the capacitor going to be as a function of time. Okay? Just like we did, or very similar to what we did just a few minutes ago, we can look at this circuit and use a relationship to essentially equate a value that is the same between the capacitor and the resistor. Remember last time we did it for a single node pair, and we assumed that both the inductor and the resistor had the same voltage across them because they were both part of a single node pair. Does that make sense? What happens in this circuit? Well, because the capacitor is in series with the resistor, right, that means they must share the same current value. And so if I have some kind of current relationship for the capacitor, that I can extend over and apply to the resistor because they are in series, right? Whatever that current is in the capacitor had better also be the current in the resistor. With me? Okay. So what that allows me to do is go in and substitute for the I that's right here. I substitute in C dV dt because those two currents have to be the same as each other. All right? And once I have done that, I can rearrange that equation so that I get dV dt is equal to minus V minus Vs over RC. Okay? Now, as I get ready to kind of analyze this further, what I'm going to do is, again, separate variables. I'm going to take everything that has to do with voltage and pull it to the left side of the equation, everything that has to do with anything else and move it to the right side of the equation. And then once I do that, I will have expressions that are set up well to integrate. Okay, so that's what we have right here. Now here's what I'm going to really point out. You might remember we did something very similar to this for our inductive circuit just a few minutes ago. But what value did I use at the lower limit of integration for the current in that case? Do you remember? For the pure forced response, we assumed there was zero initial, in the case of the inductor, zero initial current in the inductor. In the case of the capacitor, right, you would assume for a pure forced response, zero initial voltage. What happens though with this circuit? We don't have a zero initial voltage, we have a non-zero initial voltage in the capacitor, right? So that's kind of where the big difference happens between a pure forced response and a combination of forced and natural response. It's really kind of comes down to that one variable down there. Okay? All right, so from this point on, though, the steps are going to look kind of similar, right? The only difference now is, again, that VO, if you look at what we did for the pure forced response, we used a zero value there. Now we're not going to have that luxury of making that a zero value anymore. Okay? But the steps look very similar, right? We have that we could take the integral of this thing, and that would lead to natural log functions. We would still take those natural log functions as exponents of e in order to undo them and essentially extract what was in the argument of those natural log functions, right? So what that would move on to is an expression that was V minus Vs over the initial voltage V0 minus Vs being equal to e to the minus 1 over Rc times t. Okay? And if we kind of break that up even more, we can isolate just the V value. And this expression right here is actually a very interesting expression in its own right. Let me actually mention a little bit about what it says physically. It says that our voltage that we are going to have in the capacitor is going to be equal to the voltage that the source is supplying plus the difference between the initial voltage in the capacitor and what the source is supplying. And then that's going to get multiplied by this e to the power of some function of t. Okay? This is kind of interesting because look at this circuit and think about what is the steady state going to be for the switch after, or this, the circuit after the switch closes. What is that steady state going to be of the voltage in the capacitor? Okay? Careful, someone said zero. Careful. Okay? What it's going to do is eventually it's going to look like an open circuit. And if it's an open circuit, it's eventually going to take on whatever value I have for Vs. So what you see is this expression, that first Vs is essentially whatever it's getting driven to, right? And then the next piece more or less says we can subtract off whatever value it's getting driven to at time 0 so that we're left with just whatever value we have right now, right at the very beginning, at time 0, right? And so essentially what that function does is it allows you to say there's going to be this exponential curve that goes from our initial value to our final value. Kind of makes sense? Okay. Now, I actually like to break this up a little bit more and say it is possible for us to basically collect together the Vs terms. If you kind of think about this, I could distribute this e to the minus 1 over rc times t through this first expression right here, through that binomial of VO minus Vs. I could distribute that through and then collect the Vs's. And then I'd be left over with something that would be in terms of VO. And here's what that would look like. And what you will notice is the parts that have Vs in them is exactly the expression that we had for forced response in a capacitor. See that? What's the expression that involves V0? That's exactly the expression we developed for natural response in a capacitor. And so what we see here is that the total response is the sum of the forced response and the natural response. Okay? Now, I like to take it even a little bit further, and just like I did with the last one, it's interesting to see this with variables, but it might be more interesting to see it with some actual values plugged in for this circuit. Okay? So, there are some actual values. What if I have 10-volt source, let's say a 300 ohm resistor on the leg up here with a 200 ohm resistor on the R1 leg that comes down through here. Let's make R equal to 1 kilo ohm, and let's make the capacitor value 47 microfarads. Okay? When we do this, it is possible for me to plot sort of the overall response, right? That would actually be the red one right here. It's also possible for me to plot the forced response, that's the blue one, and the natural response, that's the green one. Right? And if you actually think about what it would look like to add together the blue and the green curves, what do you think that would give us? The red curve, right? That's basically what the expression that I kind of boiled this into right here, that's what that expression says, is that you can add together the natural response curve and the forced response curve, right? And you can get the overall response. Okay? This is actually, in a sense, an application of superposition. So that's kind of another interesting thing to think about. All right, so that is kind of from the standpoint of differential equations, how we go about thinking about these transient circuits. Okay? Let me actually boil this down just a little bit more right here so that I can kind of mention these two different options of viewing this. The first option is to kind of think of your total response as being a combination of forced response and natural response. Again, that's what kind of comes out of our understanding of the differential equation side that we use to develop what these equations were in the first place. But here's the news that I'm going to tell you. We are probably not going to spend much time thinking about what the differential equation viewpoint is of these circuits. And instead, I'm going to start showing you a method of how to use an equation that's more like the form that's over here on the right, that you can directly find not just voltages across capacitors or currents through inductors as functions of time, not just that, as transient responses. I can show you how you can use this same concept to come up with any voltage or current in a circuit that is set up as a transient DC circuit. But it's going to use this concept that's over here on the right more so than the kind of differential equation derivation point of view that I have over on the left. Okay? Is that exciting? Should be. Excellent.